thank you for introducing me. And I'm Davide Pettinari, and now I show you our neutronics model for the baby experiment. One of the biggest challenges in fusion power plant design is ensuring a sufficient tritium breeding ratio while maintaining structural and operational feasibility. The tritium breeding ratio is the ratio of tritium that is produced in the machine to that which is burned inside the plasma. The liquid immersion blanket offers a radically simplified approach using a molten salt. In particular, in the arc class reactor, the idea is to use as a molten salt the lithium fluoride and beryllium fluoride molten salt, so the FLIBE. And we build a lot of neutronics model, and that demonstrate an HBR that is possible to reach with a liquid immersion blanket. The three main functions of a liquid immersion blanket are breeding tritium, shield from neutrons the external region and the magnets, and extract the power density. However, experimental validation remains a challenge, so particularly due to the complexity of the tritium transport and to the FLIBE radiochemistry caused from the presence of beryllium. So here the researcher at PSFC at the Plasma Science and Fusion Center created the LIBRA experiment. The liquid immersion blanket robust accountancy is an experiment that will be a first of kind to explore and develop the liquid immersion blanket concept. The liquid immersion blanket that we want to develop is a radically simple molten salt tritium breeding blanket from a deuterium-tritium source that could provide 10 at 9 neutrons per second, and the temperature of the FLIBE is around 700 degrees Celsius, and we want to put 500 liters of FLIBE here. The ambitious goal of LIBRA is to achieve a tritium breeding ratio greater than 1, demonstrating the capability of the liquid immersion blanket to breed enough tritium and de-risking the path to a fusion power plant. The CAD shown here on the side is the LIBRA-1, the next step we will build here at Plasma Science and Fusion Center. Currently, our analyses are based on the baby model. On the baby model, we have a 14 mega electron volt deuterium-tritium neutron generation and 1 liter of lithium chloride and lithium fluoride made by natural lithium molten salt. The tritium is created here from nuclear reaction, and the tritium is transported in the salt by two mechanisms, the diffusion and the advection one, thanks to the fluid movement. The tritium is released into the gas phase, and we put inside our model helium and bring out helium and tritium in order to collect and count that one. But tritium follow two different release pathways. This one is a classic release at the gas-liquid interface, but we have another one, the permeation through the wall. So for collected and counted that, we put other helium in the other vessel and bring out that helium in order to count that tritium. Here we show our analysis. In particular, in red, we see the irradiation time of about 12 hours, and the Becquerel values of tritium release in the circuit, in particular in the outside vessel and in the inside vessel, so on the top release. In our research, we follow this structured workflow to study tritium behavior in fusion-relevant environments. In particular, we first conduct experimental measurements using diamond detector, activation foils made by niobium and zirconium, and after that we employ liquid scintillation counting to assess the tritium activity. In this way, we evaluate the total production of tritium and we counting the total number of neutron production. With these two values, we can calculate the experimental TBR. Simultaneously, we develop a neutronic and tritium transport model, a computational model, and thanks to that model, we can extract the two key parameters for our analysis: the mass transport coefficients and our modeled TBR. So, when we have the experimental TBR and the evaluated TBR, we can compare our measurement. For create our model, we use another open source software that is OpenMC, a community Monte Carlo neutron and photon transport simulation code. In particular, here we define the problem. So we set up our geometry using, for the moment, the CSG, so a constructive solid geometry. We define our materials and we specify our neutron source. So we perform our Monte Carlo simulation using random sampling to track neutron interaction, and we post-process all our data. Why we use OpenMC? Because with the OpenMC we can make a detailed physics model. We can run it on HPC, and also we can create and we can use OpenMC for a lot of nuclear application. Now I show you our GitHub repository, in particular our Libra toolbox. Libra toolbox is a Python package, and with the Libra toolbox is possible to evaluate neutron detection and neutron analysis. In particular, with this toolbox, we can post-process the data obtained from activation foils and diamond detector. We can, using neutronics tool, useful to build OpenMC model. In particular, we can use the DT neutron generator, the A235 neutron generator, and the Volt Lab model. Finally, we have also a lot of tritium tools to measurements the tritium counted. We build a neutronics model for the baby. So we first create our MIT Volt Lab, so the room where we perform our simulation, our experiment, and we construct inside this room the CSG geometry of our facility. In particular, we recreate the deuterium-tritium neutron source. We modeled the diamond detector to characterize the neutron source. We put the lead blocks that cause backscattering, and that backscattering increase the tritium breeding ratio inside our molten salt. And we model also the activation foil. Activation foil and diamond detector can be used to compare with the experimental neutron measurements with the one that we can evaluate in a computational way. So here I show you the results from the neutron flux evaluate on the surface of the zirconium and the niobium activation foils, and the neutron flux on the surface of the diamond detector. This model has also been used for safety calculation, specifically to evaluate the instantaneous dose rate inside the vault and in its immediate surroundings, in particular at the door of the vault, because we have to evaluate the instantaneous dose rate in order to ensure that the values remain within the NRC regulatory limits. So we have in that point where we have our neutron generator, the max value of neutron dose and gamma dose, but outside the vault we have a value that is less than the NRC regulatory limits. Finally, I show you the TBR measurement. On the left, we show the TBR per neutron per cubic centimeter obtaining using an unstructured mesh that is created with another open source software that is GMesh. This approach allows us to accurately model complex geometry and improving our simulation fidelity. We find a lot of tritium that is produced from lithium-7. More than 600 of tritium is produced from lithium-7. The reason why is because we have a lot of fast neutrons. Here we have our neutron source, and because we use natural lithium that contains more than 90% of lithium-7. Here we show the reasonable level of agreement, validating the accuracy of our neutronic modeling. So this is the Tritium Breeding Ratio that was measured in our experimental facility, and this is the Tritium Breeding Ratio that we evaluated with OpenMC. In the LIBRA-project, we emphasize transparency, reproducibility, and the accessibility of our experimental workflow. In particular, everything we do is open source and is fruitable and reproducible in GitHub. Each experimental run has its own dedicated repository and is possible to reproduce it with binder, and each folder has an automated workflow, and also is possible to sit in a semantic versioning all our experiments. In particular, what we did is we adhere to the fair data principle. So we want to make our data findable, accessible, interoperable, and reusable, which is crucial for advancing open science. So in our work, we have developed a 100% open source workflow to analyze tritium breeding experiments. In particular, what we want to do is the transparency and reproducibility of our experiments. Our tritium breeding ratio showed a good agreement with the experimental measurements, and additionally, all the experimental datasets are publicly on GitHub, and is possible to make other analysis, reproduce our workflow, and see our results through a DOE. And looking ahead, we are focusing on two key developments. First, we want to implement a CAD-based neutronics workflow to enhance our modeling capabilities, and after that, we are expanding into multi-physics modeling. In particular, we want to couple OpenMC to OpenFOAM for CFD and heat transfer simulation, incorporating aspects like, for example, turbulence and magneto-hydrodynamics. And furthermore, another things that we want to do is to couple OpenMC to OpenFOAM with FESTIM. That is another open source software, and is specialized code for tritium transport simulation. Here we show a first result for a first try that we make to couple OpenMC to OpenFOAM, and a first that we obtain couple OpenMC to OpenFOAM. Thank you for your attention.
You know, I can probably just talk from your monitor. So thank you very much, Davide, for a really nice talk. We've got one question already from Jake. Why niobium and zirconium foils in particular, purely for their neutron activation properties?
Sorry, can you repeat, please?
Like, why use niobium and zirconium for the neutron activation foils?
Okay, we use zirconium and niobium activation foils because it's the one that we have in our laboratory.
But what makes them good as an activation foil? Like, why do they work as activation foils?
No,
like that material.
The material of activation foils is niobium and.
No, why is niobium good? Why do you use niobium as an activation foil? Like for an activation foil?
We use that because in our laboratory we have just niobium and zirconium. When we I don't know what is the questions, but if is why is because we have that one. Is if the question is how it works, we evaluated the depletion of the materials after the irradiation, and through other software. For example, another open source software that we use for activation foil analysis is Compass. We evaluated the production of other materials, and we find a peak in a neutron flux, and we compare that with the one that we evaluate in OpenMC. It's possible to use a different kind of activation foils.